Hello, welcome to today's webinar, The Rise of FPGA-accelerated LLMs. I'm Big Data Wire editor Alex Woody, and I'll be the moderator for today's event. I've been a tech reporter for 25 years, and I've never seen anything like the excitement that large language models and generative AI are bringing to the space. We're in the middle of a technological gold rush, and it's no exaggeration to say that trillions of dollars are at stake here. The winners will be the ones who can embed this emerging tech into their lines of businesses or create entirely new businesses first. The investment in Gen AI is massive. Recent surveys say between 87 and 97% of companies are currently investing in Gen AI, which means pretty much everybody is at least starting some kind of project. The average Gen AI budget currently is about 4% of total IT budgets, which Boston Consulting Group expects to increase to 7% over the next 3 years. Why are companies investing in Gen AI? Well, it's because of the huge potential return of either automating some job that's being done manually or creating entirely new lines of businesses. A McKinsey report found that Gen AI could automate tasks that currently consume 60 to 70% of workers' time. All told, McKinsey predicts that Gen AI will generate anywhere from $6.1 trillion to $7.9 trillion in global value. Those are gobsmacking numbers, but they could even be underestimated. Amid this gold rush, AI gold miners are using a wide range of tools to see what works best, which keeps me and my fellow tech reporters quite busy. The tools that most folks have picked up and which sparked the gold rush in the first place are large language models from the tech giants and GPUs from NVIDIA. But are these the tools that are going to deliver the most gold to the miners? There's good reason to think that they will not be. In particular, a type of processor known as a field programmable gate array or an FPGA has been proven to be able to run Gen AI workloads with greater throughput and with less latency and at lower cost than GPUs. As AI practitioners build their solutions, it's critical that they have up-to-date information on the technology so they can make the best design decisions. Your presence at today's webinar shows that you are open to alternative AI stacks than what the industry says you have to run, which is commendable. Let me introduce you to today's panelists. First up will be Sartak Singh, an AI ML engineer from Google. Then we'll hear from Tom Legata, the executive chairman at Myrtle AI, a software and services company that develops AI solutions. Last up will be Nick Iliadis, the VP of product planning at Achronix, which develops the Speedster7t FPGAs. Today's webinar will provide a deep dive into the Achronix FPGAs and its benchmark results, which illustrate the performance and cost effectiveness of their processors. We'll also discuss how Myrtle developed LLM software for Achronix's FPGAs and Google's role in running all the hardware and the software. As you listen to the presenters and watch their demos, I encourage you to write down any questions that you might have in the comment section area on the website, as we will have a 10-minute question and answer sessions at the end of today's webinar. Well, that's it for me. Now I'm going to hand this over to the presenters so that they can introduce themselves. Sartak, over to you.
You're muted.
Classic. Hello, everyone. Thank you, Alex, for the introduction, and welcome again to today's LinkedIn Live webinar. I work at Google Cloud as a machine learning engineer, where I assist customers in developing cutting-edge solutions using AI/ML. I predominantly work with the enterprise customers and go-to-market teams to enable new use cases and applications leveraging traditional and generative AI. The transition we are seeing right now with AI will be the most profound in our lifetime, far bigger than the shift to mobile or to the web before it. The transition we are seeing, as correctly mentioned by Alex as well, it's a rapidly changing and exciting time in technology. Google remains a trusted partner that accelerates every organization's ability to digitally transform its business and industry. That's our mission statement, and we have been at the forefront of this revolution, offering a comprehensive suite of services and tools that empower businesses to harness the power of AI and large language models to drive innovation, efficiency, and growth. What we see here showcases a brief history of the research and innovation at Google. I was listening at the start of this week, the Nobel Prize provided or presented to the DeepMind team for AlphaFold, and that pioneering research is what led to kickstarted this whole revolution in some sense with the transformer model paper and everything that followed after that. Google continues to invest heavily in latest research and large language models. The biggest example of this is like more than 70% of GenAI unicorns are choosing Google Cloud. The customers that know the technology best are choosing us, and but this extends beyond the AI startups. We are also seeing substantial success with customers across different industries and verticals around the world. The most common form of GenAI applications are creating sophisticated chatbots that we can see, like, Walmart's My Assistant is designed to enhance productivity. Mayo Clinic is using enterprise search to help medical professionals quickly assess patient data. Morgan Stanley's Assistant supports financial advisors, freeing up time to serve clients. By next year, 20% of companies are expected to integrate voice-enabled interfaces with their dashboards and systems, which is huge. We know that AI adoption in enterprise will surge in coming years, but how much is really what's staggering. You can see this Gartner's report, which is predicting by 2026, 80% of enterprises will have used GenAI via API or models, or have deployed or developed GenAI-based applications in production environment. And the production environment is the key here. 15x growth in just 2 years. Things are changing rapidly, and this figure was just 5% in 2023. We celebrated Gemini's 1-year anniversary this week, and a lot has changed, and feels like such a long time ago that Gemini, which is the multimodal and the greatest model family that is coming out of Google, is just 1 year old. And the top GenAI use cases that we are looking here was collected from a survey in the leadership cycle in the next event that happened last year. And we can clearly see that, as I was mentioning earlier, customer service and chatbots dominates this category, but software development productivity, general efficiency enhancements by automating mundane and regular tasks, data analysis, content creation are other major areas in which the companies are actually looking to invest. And that's where I would love to showcase a really quick demo, which is actually from the short demo here. What we're using is a predictive and a generative AI together to proactively monitor fraud activities, fraud detection, spam detection. All of these things have been there for long, but like what nuanced or enhanced experience for a customer that can be generated using GenAI is kind of showcased here, in which as opposed to strange or untrusted emails having to navigate across multiple links and several platforms to resolve a fraud issue, what you can do is you can have a chatbot to help essentially solve that problem for you. The one thing which I would like to talk about before talking about Google Marketplace is like, what are the key challenges? Like we have been seeing these demos and applications for some time. The key challenges that I personally have been seeing in my territory and sphere of influence on GenAI application is cost and latency. So for high throughput requirements or small batch sizes applications, the cost and latency issues become very prominent. Another key challenge is like this landscape itself is evolving at a pace that I have not seen in my 10-15 years of working in this industry. The ability for a company to be flexible and experiment with different orchestration layers, different deployment infrastructures, different models, to create better applications for their end customers is where I see a lot of companies struggling with, and we are trying to create and provide solutions for that. The example of this is where all of us are together here. Like we provide the infrastructure for the, for example, for the Achronix platform that we will be hearing about next, to procure and extend the platform for post-processing things that can be used and leveraged using Google Marketplace as an example. You can buy such platforms and solutions from Google Cloud. Google Cloud can help accelerate this digital transformation using Google Marketplace, which is something that is pretty unique, and also provides an ability to scale and simplify procurement processes for the organizations to fulfill some commitments and provide cloud solutions which are not apparently available within the product suite that GCP is offering. Having said that, I would pass on to Tom to take you to the rest of the discussion. Yeah.
Okay, thanks, Sartek. As Sartek said, I am executive chairman at Myrtle, which means I'm on the board, and I actually have an operating role in the company. However, I am the sole Myrtilian here in the United States. Myrtle is, in fact, a Cambridge, England-based company who accelerates specific machine learning workloads on FPGA. We've chosen FPGA for two reasons. Reason number one is that our products are an optimal mix of hardware and software to get maximum performance. And as workloads change, and they often do, we need to reprogram both hardware and software in a rapid fashion to get back into production quickly. And so FPGAs offer us that capability. The second reason is the chart that you see to the right. If you are latency sensitive, FPGAs tend to excel in small and medium batch sizes, medium workloads, medium models, until you get out to larger models, and then the parallelization of a GPU will actually start to exceed our capabilities on throughput. So our sweet spot is on the left, where you are actually sensitive to latency. We have products in fintech. People are actually trading today on our fintech products, buying and selling stocks within a specific latency window. That model has, in fact, actually worked its way into network security. We have recommendation models, and we're now actually going to talk today about our speech model, which is actually implemented on the Achronix Speedster7t. So up to date, most of the transcription, probably 90% or more, has been run in a batch mode. Audio files come in to a cloud service provider, they're transcribed in a batch mode, and the transcriptions are sent back to customers. If in fact you want real-time natural language processing, low latency significantly aids to user comprehension. This is actually a quote from a CTO of a company that we're working with. And there is a latency window, kind of the industry sort of agrees that it's the 300 to 500 millisecond latency that makes natural language processing, real-time natural language processing, more comprehensible if you're in that window. Okay, so what we did first off is we took our transcription product and we said, okay, well, we got to make sure that we're in that latency window. And so we set up 8 of our transcription cards in a server in the Achronix virtual lab in Santa Clara, California. And we entered the internet portal in a Google Cloud portal in Los Angeles. So we literally went from Southern California to Northern California end to end to measure latency of transcription. We had 8 boards in there. 6 of them were our base model, which will actually simultaneously process 2,000 streams of audio. And then our large model, 2 cards of our large model, which will actually process 500 streams simultaneously, which gave us 13,000 streams that we were running from Southern California to Northern California, transcribing, and then back to Southern California. And you can see the measured latency over a 30-day stress test. And so the mean latency of the large model was in the 180 millisecond range. The mean latency of the base model, the smaller model, was in the 170 millisecond range. And the difference between these 2 models is really word error rate. The large model will give you substantially better word error rate at less capacity than the base model. because most of the hyperscalers are set up to run in batch mode, we actually went out and measured their mean latency, and it was in the 800 plus millisecond range, which sort of makes real-time natural language processing a bit choppy. Okay. So this is what I like to call my golf chart. Smaller is better here, lower is better here. So the green bar down below is our large model, and you can see with the English language files that we were sending up there, we were achieving around a 3% mean word error rate on 500 streams being processed simultaneously. The 2000 stream model is the yellow bar up above, and that was actually achieving somewhere around a 3.7, 3.8% word error rate, but at a substantially higher capacity. And in the upper right-hand corners are where we were actually measuring the latency for the hyperscalers in their products that are offered today. These models, the actual large model is very competitive with the Whisper benchmarks. Their best benchmarks in the sub 10% range for word error rate. We're right in that range. So this is a very, very competitive model. Okay. Because we have such a massive capacity of transcription on these cards, if you want to set up for a peak workload of say 64,000 real-time streams that you want to be able to handle at once, you would use far fewer cards, far fewer servers, far fewer racks, which take up far less volume, dissipate less energy, less cooling is required. So in addition to the latency that we would actually provide, we give a TCO that we actually calculated at about 50 times improvement on a 3-year operating model for that 64,000 streams that we actually just calculated. Okay. So these are our products. Today we have the 2 ASR models. The 85 million parameter model will give you the 2,000 simultaneous streams. The 200 million parameter, 196 million parameter model will give you that 500 simultaneous stream capability. Today we're going to demonstrate for you a Llama 3.1 large language model accelerator, the 8 billion parameter model on a single Speedster7t, transcribing data, talking to Llama 3, and Llama 3 actually talking back. And then right after the first of the year, we'll be interconnecting 4 and 8 boards so that you can run the 70 billion all the way up to 400 billion parameter model. And in the first half of next year, as we get to the 8-board system, we'll be changing our software stacks so that you can pretty much accommodate any large language model out there with our 8-board system all the way up to that 400 billion parameter model. So what I'm going to do now, we're going to show you a little demo. We have 2 cards running. We have an ASR card, a transcription card, running the base model, and it is actually feeding a Speedster running the large language model accelerator running Llama 3.1. And we have an engineer in Cambridge asking the large language model questions. The large language model is responding, and we're just synthesizing today and using an x86 synthesis program, but we'll be actually accelerating that in the future. What you'll notice on this thing is the data set that we actually trained this model on is fairly standard English. So a lot of the tech terms, this thing will actually kind of, have a little trouble pronouncing, like instead of FPGA, sometimes it will say FPGA or something like that. But you can actually see how this thing would actually perform. So Nick, if you want to run the demonstration, go ahead.
What is a vector path card?
Vector Path Accelerator Card is a high-performance compute card developed by Achronix and Myrtle, leveraging Achronix's Speedster7t FPGA for accelerated computing in AI, ML, data analytics, and HPC. It offers high bandwidth and efficient performance.
What AI ML workloads can be run on a vector path card?
Vector Path supports AI/ML workloads like Cayman-Osser, low-latency speech recognition, and Cayman-LM, natural language processing. It's ideal for conversational AI and fast code completion due to its low-latency capabilities.
When would it make sense to use an FPGA for LLM inference rather than a GPU?
When low latency is crucial and low batch sizes are necessary to meet latency constraints, FPGAs are preferred. Examples include conversational AI and fast code completion.
Write me a limerick about AI.
There once was AI, so bright, processed data with speed and might. It learned with each test and passed with finesse. Now it's a wonder in sight.
So that's actually a cropped file from about a 3 or 4 minute demonstration we have. I didn't want to bore you with the whole thing, which is why it kind of started mid-demonstration. But it kind of shows you how speech is digitized. It goes through a WebSocket API into our transcription engine, which then feeds the LLM accelerator, and the LLM accelerator responds. So that's how it actually works. The reason we actually chose Speedster7t is it's really an AI optimized architecture, which really starts with something that they call machine learning processors, which are in fact processors that are good at vector manipulation, vector multiplication, vector arithmetic. There are some 2,560 of these MLPs scattered around a Speedster7t. We actually use about 90% of them, more than 2,300 of them in our products. And the way we route data to them is in a hardened 2D NOC that they have in the upper layers of metal, which routes data efficiently east and west and north and south. And so we can get all of the weights and data out of the high bandwidth GDDR6 on chip across that NOC and into MLPs, so that we can run this thing at a very high clock frequency, a fairly high F max. So that's how we actually achieve the performance we have. I'm now going to turn this over to Nick Iliadis, VP of Products at Achronix, who can give you more detail on the actual architecture of the Speedster7t.
Thank you, Tom. And first of all, I want to say that there's been a great working relationship between Myrtle and Achronix. Tom and I actually worked together in previous lives, so we go back quite a ways. And I also want to thank Google. They've been a great sponsor, and they've allowed us to show them how well our products work for addressing solutions in their marketplace. So next slide, please. So first of all, let me introduce Achronix. We are a manufacturer of high-end FPGAs. Our products today are named Speedster. We have currently shipping 2 members of the family, the 1500 that Myrtle is using, and a smaller version that can be used for, let's say, edge applications. It has all the same capabilities, but it's just basically a quarter of the performance. Our products are the most advanced high-performance FPGA architectures out there today. As Tom said, they are optimized for data acceleration, and they include advanced efficient data transports, which I'll go into more detail later. The other thing that's unique about Achronix is that the same FPGA technology we use to build our devices, we also license as IP to customers that want to incorporate that FPGA technology into their ASIC or SoC, meaning they are able to take an FPGA fabric and embed it inside of their device. And rather than having an FPGA outside, it's inside, attached to all their logic to provide the flexibility of an FPGA, but within an SoC. And today, our customers have shipped over 15 million of these cores in their products across telecom, high-frequency trading, and automotive. And finally, we provide the FPGAs we sell on PCIe cards that can be used by our customers for doing evaluations, development, or even shipping in as a product. And finally, all this is supported by our tool suite that provides synthesis, verification, timing, and programming, as well as debug once the design is in place. So let me talk a little bit about the capabilities of our architecture. The Speedster7t family includes what we call our machine learning processor. In the case of the 1500, this provides 71 int8 teraops or 142 int4 teraops. So that's quite a large number of operations in the integer space. I'll talk more about that in the subsequent slide. We also have what we call our 2D NOC. This is a unique architectural capability that only exists in Speedster. This is a grid of high-speed channels that crisscross the device and allow data transfers to occur at very high speeds between the periphery of the device, where the I/O and memory exists, and the internals, or within subsystems within the internal part of the FPGA to do rapid data transport. The device that we're working with today has 100 gig SerDes that provide 100 gig Ethernet up to 16 ports for 1.6 terabits of capacity that can run all the way up to 400 gig. And we also have 2 PCIe controllers, both at by 16 and by 8, doing Gen 5. And finally, the device uses external memory, GDDR6 memory, that provides 4 terabits of bandwidth. The GDDR6 memory uses the same memory technology as HBM that is used inside of the GPUs today. But unlike the HBM, it's external, and then customers can decide whether they want to populate all 8 controllers or use a subset if they don't have the bandwidth or capacity requirements for that particular design. Next slide. So just drilling a little bit into our 2D NOC, you can see here, zoom into the intersection of 2 of the channels. At every intersection, there are what we call NOC access points. Think of these as on-ramps and off-ramps from a superhighway that is above the fabric of the FPGA and allows you to move data at 512 gigabits full duplex or terabit of capacity between a NAP and either the external controllers that control GDDR6, Ethernet, or PCIe, or between logic that is in different port sections of the FPGA without having to use the actual FPGA resources to route the information between the blocks. So it gives you a lot of flexibility. And there's 160 of these NAPs spread across this 8x10 grid, and each of them have full access to the entire flat memory space of the device. So it provides a very easy to use design methodology, and it eliminates the floor planning. In any of these devices, the memory hierarchy and bandwidth are key, because at every level of computation, you have different quanta of information that you want to be using. Down at the FPGA fabric, we have 2 registers per 6 input LUT, so that you have local storage. There's the MLPs, the machine learning processors, have 2 kilobits of LRAM register files, as well as 72 kilobit of local RAM to use for mathematical operations, such as weights that are used in neural networks. And then you get out to the GDDR6, which provides this very fast, fairly dense memory, 4 terabits to 32 gigabytes. And then finally, we also have a DDR4 or DDR5, depending on the device, that provides bulk storage if you want to have some large databases that you want to move in and out of the device as needed. Next slide. So talking about the machine learning processor, this is a high-level block diagram of it. The thing that's very important about this is that it is fracturable, meaning that you can take a single MLP and use it in different number formats depending on the dynamic range or resolution that you need. So in the case of integer, we can run as a single integer 32. You can then fracture it to run as 2 integer 16s. 4 integer 16s. You can run it as 8 integer 8s and 16 integer 4s. As well as we support floating point formats, floating point 24, 16, and what's called brain float 16. And one unique capability that we have is what's called block floating point, where you can basically take 8 mantisas and share a common exponent. So this gives you the ability to scale dynamic range in a floating point manner, but have the tops that are available through the integer. So basically, you have the same tops teraflop performance as you would have teraops performance because of this block floating point. Then the local memories, like I said earlier, please go back. The local memories are 2 kilobits for this register file that would be used to hold intermediate values, as well as 72 kilobits that are used to store things like weights or potentially intermediate calculation values. And then the blocks are cascadable because they exist in a column architecture within the FPGA. You can cascade multiple of them together to create larger math engines. Next slide. And you can see that here, where we do both vector and matrix multiplications in the device. You can, like I said, create these larger arrays by just cascading these devices using the internal cascade mechanism, or use the fabric to build larger 2-dimensional arrays. And you can see here these are have the ability to recycle data, so you can get a lot of data reuse. And the beauty here is future proofing. FPGAs are highly malleable, highly reprogrammable. So any architecture that you can envision that can be instantiated on the FPGA will allow you to have future proofness for any type of math engine that you want to create. Next. So we provide a GEM core. This is a matrix tensor core that is built out of our MLPs in a stack. It has a local VRAM and then can be used to do the dot product between a matrix A and a matrix B. And then when you take these, you can instantiate them in an array to build up a machine learning network. Next slide. So one of the things that we've talked about here is the latency capabilities of an FPGA. And this slide really shows why that is when you compare the architecture of a machine learning, let's say a tensor array in an FPGA compared to how a GPU is architected. In our case, we have these high-speed channels, the 2D NOC, that bring data in from the GDR6s to the tensor cores. And then as the tensor cores complete their calculations, rather than sending the information back to, let's say, a common memory, they're able to send the information directly to the next tensor core in the pipeline, and therefore only do it in one clock cycle. Whereas in a GPU, because this hierarchical memory that is used by the tensor engines and then shared between different levels of the hierarchy, as you have to reach into the memory to get some intermediate values, you could incur up to 500 cycles of access. So in the left, you can see here it's a very kind of flow-through architecture where the activation functions come in, the intermediate values get shared between the tensor cores, and therefore you're able to do this very low latency. Next slide. So as Tom was saying, we currently support the Llama 3.18 billion model on a single card. And then you can put up to 8 cards per server, and that would give you up to 10,000 tokens per second per server. And then you can take 4 cards and using 100 gig Ethernet, you cluster them together. And what this allows you to do, just like NVLink is used by NVIDIA to cluster GPUs together, we use 100 gig Ethernet to cluster our FPGAs together to create even larger compute engines that are working on a common data set. So you can then put 2 of these clusters into a server, an 8-slot server, and get up to 1,000 tokens per second per server. And here are the links if you want to get started with Achronix, as well as access the Myrtle Cayman documentation. They can be reached over the internet. So with that, I am going to turn it back over to Alex to take us to the next portion of our discussion.
All right, thanks, Nick. That's fascinating about the FPGAs. That was a great presentation. So we have a few panel questions here that I'm going to ask our presenters. And Nick, we're going to start with you. What is the training procedure for the ASR and the LLM models with the FPGAs? Is it the same for training the GPU-based ones? Yeah,
it is a very similar procedure where today FPGAs are really good at doing inference, but they're not really capable of doing training because of training typically these very large data sets. So for us, the training is done on a GPU just like it is done for other AI models. But the training model is then extracting the weights, the parameters that are going to be used by the FPGA. So there is a transformation from what comes out of the training to what would then get loaded into the FPGA's GDR6 memory. But the procedure is similar. And in this case, Myrtle does make the training repository for their ASR available on GitHub. So customers can actually take the base model or the large model, depending which one, and uptrain it, meaning that then they can augment the training that's already comes with the model out of the box, let's say, with additional information. As an example, recently we have a customer engagement in China where the customer wanted to have a mixed language model, meaning that it was both able to do English and Mandarin. And the Myrtle team took a Mandarin language data set and trained the existing model, the English model, with Mandarin and turned it into a bilingual model. I was actually very impressed at how quickly they did it. I think they were even like surprised at how well it worked as well. But this is a very, it's just a testament to the flexibility of the Myrtle model running on the FPGA. All right. So basically, you're not training the model at all on the FPGAs, right? That's done on Correct. GPUs. Yes. All right. Great. Let's go over to Tom for a question for you. So there's a lot of vendors out there selling lots of transcription services. What's the advantage of Myrtle's approach here?
So our transcription product actually has 3 advantages. First, the unrivaled capacity per card, up to 2,000 streams transcribed simultaneously. It gives you the ability to do a lot of transcription without a lot of hardware. Second of all is power. A single card processing 2,000 streams is right around 120 watts, which is about half of what the plug-in GPU cards are doing these days. So it actually translates into superior TCO. And then, as we talked about earlier, if you want to we talked about transcription today. 90% of it actually being run in batch mode, where files come in, they're transcribed in batch and sent back. The amount of real-time processing that is emerging is starting to grow fairly significantly, and with that comes the requirement for latency. And I demonstrated earlier that unless you have low latency, the stream coming back to you is not going to be terribly comprehensible. So, our advantage is capacity, power, and latency on our transcription product.
Great, thanks. And another question for you, Tom. These LLMs are getting huge. We're seeing models up to 400 billion parameters in size. I've heard rumblings that we're going to be into the trillion soon, perhaps. So how do we cope with this growth?
So the current product is actually designed to be cascadable. So the single Speedster7t card will run the smallest of the models, the 7 billion parameter model. But as Nick said, interconnecting with 100 gigabit Ethernet, 4 cards gives you 80, 8 cards will give you 400. We can handle, the fairly large models by cascading cards together. And as I had said earlier, as we get into next year, we're going to be changing the software stack so that we can handle, pretty much any large language model that you want up to that 400 billion parameter model. And if it gets bigger, then we'll just have to cascade more cards. So that's kind of the way we've actually addressed that right now.
All right, great. And we have a question here for Sartak. What are the major challenges to the widespread adoption of generative AI applications across different industries?
Yeah, it's a pretty broad question. So the practical application, so one of the things which I mentioned earlier as well. So the deployment, scalability, and integration of these applications that have been developed is one of the big challenges. And what we have seen at the early stages, which is like a year and a half ago. So there was a lot of talk about models individually and the applications which were being created out of them. But increasingly, the model conversation to a RAG, which is a retrieval augmented generation based application, to an agentic application framework shift that we have seen, especially in the enterprise landscape, that requires companies to have resources and integrations created with their backend data. Data still remains the king. There's still a lot of challenges around data scarcity and quality, with safety and responsible AI that at times there's a lack of transparency. It seems in terms of the output that we're getting out of these applications. So how to ensure that the safety and responsible AI considerations, which Google AI principle emphasizes a lot on, are integrated in these application development cycle. That's also one of the key challenges, because I've seen real examples of developers and teams working on these applications, and as they are ready for deployment in production, someone from security or governance teams would come in and throw a wrench around it, and that's why we take all of these things pretty seriously and have this conversation as a start of development process. And as it is relevant to this conversation today, latency and real-time performance then becomes a really important thing, especially if it's a customer-facing application. Even a second delay in the response time, it's at times not acceptable, and that's where we are collaborating and providing these multiple ways of developing these applications. So there is standard tools and solutions and services like Vertex AI platform, where you can go and develop these applications, use Google first-party models like Gemini and other models. But everything which is there on the open source, from Hugging Face integration to Model Garden, where you can use open source large language models, to various ways of deploying these applications for specific use cases, like where FPGAs would be really applicable, is where Google Marketplace comes into place. So that's that's the overall I can talk about it. Yeah.
Yeah, and just to build on Sarkat's comment here, we thank Google for allowing us to provide this service through Google Marketplace, because I think having a different mechanisms by which we can deploy these models, I think, is important. And the fact that it does have a value proposition for certain use cases, I think that may be different than what can be available from other platforms, is also appealing as well. So for low latency type of responses and workloads, I think this is it's a nice option for customers to have.
Yeah, I would agree. And Sartak had mentioned something about the importance of good quality data. That's something that I write about. It feels like every day at Big Data Wire, just the importance of data management, data governance, getting high quality data. But that's not why we're here.
Mm-hmm.
That's not what we're here to talk about today. I just want to remind the audience members that if you have questions, you can type them into the comment section on the screen. Next, Nick, we have another question for you. Based on all the information in the press, it seems like GPUs are the dominant architectures out there. But GPUs, they have a lot higher compute performance with more arithmetic resources running at higher frequencies than FPGAs. So how can FPGAs with fewer resources running at lower frequencies outperform a GPU?
Well, first of all, in terms of the frequencies, our MLPs can run at 800 megahertz. So this is not too far removed as to what the tensor cores are running with in a GPU. And as I shown earlier, we have an architectural advantage in certain workloads where we can outperform the GPU because we can run at low batch sizes with very low latency. So we're not here to say that, hey, across the board, an FPGA can outperform a GPU. But if latency, power efficiency, and cost are things you want to optimize, that's when an FPGA is something that needs to be looked at. Because obviously, as I design microchips, right? A Blackwell is what's called a full reticle device, meaning it uses about almost 800 millimeters of silicon. So first of all, that the yield on that is very low because you have some defects. The power on that is very high. Yeah, great, you get a lot of performance, but it's a big chunk of silicon and performance you want to buy. Where at FPGA, we can right size it to whatever application you need. One of the things here, we have our embedded FPGA technology. So if you wanted to build a small neural network inside of a device using FPGA technology, you can do that, right? So again, we're not trying to say, hey, we're better than GPUs across the board, but in certain areas where latency and power and costs are factors, there is where an FPGA can be considered as an alternative.
Okay, great. And next question's coming in. The technology and the total cost of ownership for automated speech recognition and LLMs, and the performance looks good. How can I get more information and a demo?
Well, you can reach out to ourselves, either Achronix or Myrtle, either one of us, and the links that are in the page there, and or even through the LinkedIn, you can leave comments here, and we'll reach back to you. And we have our demos ready to go on the cloud.
All right, and we have another question for Sartak here. What are the latest advancements in the GenAI application landscape for enterprises?
Oh, that's again a great question, and not sure how many have seen the news. Hot out of the press, Gemini 2.0 Flash was launched today. So that's the latest model in the Gemini suite of models, and it's much more performant than the earlier Flash model. It's even better than the 1.5 Pro, which was the top of the line model that we had earlier, and it's much lighter and has a faster response time. It has increased the number of modalities and output. The reason I'm talking about that is to showcase that one core area that we are seeing in the advancements on GenAI application landscape is these models becoming better over time. So every other day you see that the leaderboard on Hugging Face will keep changing, and these newer models are much general purpose. Large models are getting better over time, and that trend continues to. I see that trend would continue, and the size, the token length, the context windows, all of those things are also increasing, while the costs and the latencies are reducing over time. That's what I've seen in last 1 year. Okay. Another important things on the model front is like task-specific smaller models, which are more industry-focused, like MedLM, for example, or MedGemini, or MedLM basically is large language model which are tuned to provide better responses for certain industries, like medical, like healthcare, life sciences, and just 1 second. Sorry. What was I saying? Yeah, so there are these another set of events that we're seeing on the models specifically is the task-specific, industry-specific models being created, and Google is also doing a lot of development on that front. Then there are these even smaller, distilled, fine-tuned, even much more open source kind of models, which can be installed in a much smaller compute requirements, and that's where I think a lot of FPGA-based and other kind of specialized use cases would come to light more, and that's my personal opinion. In terms of other advancements, like that's model is just one piece. Like we have seen this in the data science worlds. Like the data science models eventually is a very small component of the whole big application landscape, which includes LLM ops, which includes your data and your integrations and your tool calls and function calling and the frameworks and the orchestration layer. And I can go at length on what all is needed for creating a really good application in production. So there has been advancements in all of these things. The platforms are providing a lot of services out of the box, a model as a service, RAG as a service, frameworks as a service, hosted frameworks. You can have Llama Index hosted on Vertex AI, for example. So a lot of these managed services are coming into the landscape as well, which is essentially aimed at simplifying the process of application development for enterprises, because this is a new space, and we see there's a overall lack of expertise within the organization to develop such applications, and hence these solutions that we are seeing in the market are simplifying that process. And if you want to add anything, Nick or Tom, please feel free.
Well, just one other point, I think let's say domain-specific training, I think, is important here, right? Where you could take a base model that's been kind of trained, let's say, generally, and then uptrain it in specific areas that make it more, expert in those areas. So I think that's one key capability. And with the Myrtle models, we have that capability where you can take the base model, and then if you want to, teach it something in pharmaceuticals, it teaches something in, engine repair, whatever the case would be. You can give it more training than what comes out of the box.
All right, great. Then we have another question here. What are there any other benefits for mapping ASR and LLM workloads to FPGAs versus GPUs or any other hardware architectures?
Tom, you want to start with that one?
I guess I can. I mean, primarily as chatbots emerge, as real-time natural language processing becomes more prevalent, latency is going to be very, very important. And as I showed earlier, latency is in fact, one of our strengths when it comes to actually processing in real time. So I would say that's the real benefit. As long as latency is an issue, I mean, it's gonna require FPGA if you want to actually do it in real time.
Okay. Great. I've got a question, probably for you, Tom. We've heard about a lot of great tools here today, FPGAs, the Myrtle software and services. What types of solutions can people build using all of this? And what other I guess what other knowledge do people need to bring to the table here to build something and get it out there?
Yeah, interestingly enough, we actually came out with products and technology targeted at specific verticals. And the three verticals were, recommendation, fintech, and speech. However, we do have tools that allow people to bring a model in, run it through our tools to determine whether it will fit one of these networks, determine what its cycle and bit accurate performance are. And that's how we actually ended up with network security on the fintech product. It wasn't designed for that, but people came in with those models. We ran it through the toolkits and found that it did an actual good job in that particular area. So if you have another vertical that you want, we can certainly run it through our tools to determine whether it'll fit on any of our models today, or we could actually build something for you in a particular vertical you want to target. So
let me expand on what Tom was saying here. So our FPGA, as we showed you here, is not only a high performance AI ML compute engine. It is also a high performance networking platform as well, because we have these high speed Ethernet links and the programmability of our fabric and our 2D NOC. We're able to run 400 gigabits full line rate on the device as a DPU. What this allows you to do, as Tom was saying, for things like network heuristics or network intelligence, you could be running a standard DPU function and then also having a small neural network in the same device that's looking at information coming off the traffic types, the protocols that are being written, looking for any flows that are anomalies, and basically alarming the network operator that, hey, I'm seeing something that is not normal in this network, right? So now you have this network intelligence that's built into the network using AI/ML. Additionally, low latency. If you're in a wireless infrastructure, a lot of the new algorithms are being developed for doing things like channel estimation, power optimization, load balancing, are using AI/ML as the backbone to make those decisions. When a network is seeing the change in the flow of traffic, let's say there's a commuter going on and the traffic is moving from one geographical area to another, the AI/ML can start moving compute resources to where the traffic is, powering down systems that are where the traffic isn't, and providing safety. And a lot of that has to be done in real time because you're looking at real time type of events. So these are other areas that we are working with other customers to provide solutions for using our FPGA platform.
the interesting thing, Alex, is many of our customers actually prefer FPGAs for two reasons. Number one, they've gotten very capable. They've grown. They can accommodate quite sophisticated models. And number two is workloads change. And as workloads change, you can change an FPGA and be back in production in a very short period of time. So a lot of our customers are very committed to FPGAs for inference as they're moving forward. So that's kind of a sort of an aside to that question.
All right, great. And we have a question from the audience here from Hazim Mohammed. Do you think that there will be high demand for FPGA engineers, or will the AI write its own firmware?
Yeah, I guess I'll answer that one. At the end of the day, you still need to have somebody that thinks about what the problem you're trying to solve and be able to, break it down into its component parts. Right now we still need engineers. Thank you. We will for a while. Yes.
Yeah, we actually do use AI for some of our software development, but you cannot trust it. When it comes out, we still have to debug it. We still have to tune it. We still have to do the things necessary. So I think in the future, you're going to see a combination of humans and artificial humans working together to do these things.
And let me give you a parallel, Azim. Removing the FPGA, just normal software engineers. We have tons of developers here at Google, and you might have seen the recent announcement by Sundar Pichai, in which it mentioned that 25% of all new code that is being written at Google is AI generated. But that demand is not going down. So I highly doubt that the engineers' demand will go down in future as well.
Yeah,
I
if
would
anything,
say
it's going to increase.
software is a gift that keeps giving. When I used to run engineering organizations, software was that investment that you always had to keep putting into it because there was always a continued demand for features and functionality. So, there's going to be demand.
There is one more aside to that, and it's not that we're actually using AI to create FPGA net lists. However, we are developing and creating a fairly rich library of inference-based net lists that you can run through our toolkit to determine if a model that you have is suitable for one of these architectures. So, as we continue to generate these net lists, we're generating them with humans, but we're actually using our software to determine whether your models can actually run on these net lists and take advantage of what we've done for other opportunities. So,
okay, I've got one more question about FPGAs for Nick. How's it possible that your FPGA-based implementation of large language models can outperform GPUs while having only a fraction of the amount of on-die memory?
Again, this comes back to if you're focusing on that latency aspect, saying, okay, I'm going to be running a batch, between batch 1 and batch 64. That's where our architecture of being able to move data in and out of our device very fast allows you to use the local memory. In this case, it's 192 megabits very efficiently because you're only working on a fixed batch size. Again, just as that graph that Tom showed, once you get out to these large batch sizes and latency is no longer a concern, the on-chip memory of the GPU is going to obviously outperform us. But if we're down in this, between 1 and 64 batch size, there's sufficient memory on the FPGA to do the same workload that the GPU could do.
Okay, one more question for Sartak here. What are the future research directions for Google and its GenAI large language models? Any plans to develop new architectures or modalities?
I feel like I answered a bit of that. So the future of research, okay, so essentially when we look at Google's approach now, we can break it down into 3 major areas. So like the fundamental research, that is the investment in DeepMind and all the new advancements of the state-of-art LLMs that are coming out, that is going to increase. And Gemini 2.0 is a great example. So Gemini was the first natively multimodal large language model, at least largely used in actual applications. One of the major advancement, within a year, what we have modalities, just not as an input, but we have multi-modalities in output now in 2.0 Flash. There is a native so your tools and extensions, like people have done and created these applications would know, like tools, function calling extensions is a ways to create these applications more interactive. And this agentic framework, what I am seeing right now is like this native tool calling capabilities going within the model rather than you as a developer have to create it. So for example, like if you want to get the weather information, so you will have to call a function which will call a weather API, and then you will get the update and provide that as a context to the large language model to give a response to. Native tool calling and functions is the model itself would have this native integration to Google search, for example, to see if they have the right information context to provide the answer which is more factual. So factuality remains a concern. It will remain a concern for some time. So that is the fundamental research and increase in modalities and stuff that continues to happen. And the other major approach of Google is like we are always emphasizing on responsible AI. So explainable AI, the security and AI framework and the principles around it, all of this is in public domain. We have had a lot of fairness, safety and transparency conversations. We are integrating all of these services to our big applications. The biggest advantage I think that Google has here is like there is billion users for lot of these applications that are already in production where these large language models and Gemini is getting integrated. Search, YouTube, and your workspace, and all of this is getting a lot of feedback, and that's where I will come to the last one, which is like the openness and collaborations, and that's where again, sharing research findings and collaborating with the community, collaborating with our partners like Achronix and Myrtle here is like the Google approach would be same here. And in essence of time, like I will just quickly talk about like architecture-wise. I think agentic architecture and transform-based architectures will continue to evolve, but like I'm seeing a lot of hybrid architectures where leveraging strengths from different places, sparse activation models and things like that are also becoming very prominent, where there's been a lot of research in smaller companies or creating some solutions as well. And I will hand it back to you, Alex. I think there's more I can talk about it, but I think we're running out of time.
Yeah. I mean, it's a very rich space. There's a lot going on. These tool chains are just being created kind of as we speak, right? So a lot of fun to cover it. We're getting close to the end here, but we have time for one more question. What's the difference from a user point of view between running these workloads on GPUs versus FPGAs? Nick or Tom, you want to take that?
Again, it's what does your workload require, and so if you're running sort of a small to medium batch workload, latency is tantamount, power is an issue. These things where FPGAs accelerate, where the models that we've created actually accelerate, great. If you need massive amounts of throughput with very large models, then you're probably going to want to go to a GPU and run it on there. So it really sort of depends on what your workload requirements are as to what platform you actually run on.
All right, thanks. Well, that's going to wrap it up for today. Thank you for attending our webinar. I hope all the attendees got everything out of it that they were expecting and realized that there are good alternatives to GPUs for GenAI workloads. We'll have a recording of this webinar up soon, and we'll send an email to you. So please keep an eye on your email inbox. Thanks again for attending, and goodbye.
Thanks, everybody.